And concerning the terms which is proportional to the divergence of the axial current, and it has already been mentioned by Matteo that this divergence of the axial current is proportional to the, so it is, that is broken. So it is not conserved because of mass terms, because of quark mass terms, but in general it's quite small and should not be really, I would say, quantitatively important for the calculations of the quantitative freeze out. On the other hand, that if the final hypersurface is the freeze out, this divergence of the axial current is different from zero only the very late stage. Therefore, one expects that it should not play a quantitative a major role in correcting, say, the helicity or the spin polarization vector expressions.
Xu Guang, what is your take? You wanted to add something unrelated, or
maybe unrelated, but maybe also related. I'm not sure.
Okay.
Yeah, I think the question about the whether it's different or is there a relation between the spin chemical potential and the actual chemical potential is interesting. I feel confused because suppose we formulate a theory like hydrodynamic theory with spin or with actual current. In this case, if we introduce the spin chemical potential and also the actual chemical potential, do they play some similar role? If we choose the canonical spin tensor, or are they really irrelevant, independent, or are they somehow?
Well, they are independent. I mean, it is true that, as you pointed out, that the canonical spin tensor is the dual of the axial current. However, if you write down, so if you, for instance, if you take the expression shown by Matteo with the axial chemical potential, which is a scalar or pseudo scalar, okay, suppose it's a scalar. The scalar is coupled to the axial chemical potential. This scalar will multiply the Levi-Civita tensor, but it will not contract with the indices. So, in other words, the conservation of the axial charge is an additional conserved charge compared to the angular momentum, and therefore they have different potentials. So I don't like the adjective, say, chemical with the spin. So spin is spin. So they have different potentials, and therefore, say, from the point of view of say conservation laws, they are independent constraints. In other words, that if you want to say write down the operator which maximize the entropy with constraints, the conservation of the axial charge and the conservation of the angular momentum are independent. And even if you have a independently conserved total spin, as Wojtek, for instance, proposed, there would be different constraints, so independent, and you have to enforce them with different potentials.
Yeah, okay, let me first make sure I understand what you are saying. Basically, you are saying that the actual chemical potential is conjugated to the zero component of the actual current, the density. And the spin potential is actually conjugated to the vector component of the actual current, which in the canonical case is spin.
Yes, in a sense.
Those are two independent chemical potential.
Yes.
Yes. Okay. Good. Thank you.
I'm not sure I totally agree with all the statements. It's also very confusing to me. I mean, I think we have to be a little bit more specific, perhaps, because I think there's no general answer. When we talk about axial current, for most of the time we are thinking about perhaps massless fermion, underlying massless fermion, because that's the only situation when you have a classically conserved axial current. If you're thinking about, for example, massive fermion, there's no even classical symmetry to start with. I don't think we can talk about axial chemical potential at all, right? And you know, if we think about, you know, massless fermion, let's say Yukawa theory, massless fermions coupled to some scalar field, this is a relatively clean situation where you have a conserved axial current. We can talk about axial chemical potential. And angular momentum is a totally different, separate situation. Angular momentum is conserved for any theory.
Right. No, yeah, I agree. I agree with what you're saying. This is why I think if you have a conserved axial current, which you can say somehow, which can include the Chern-Simons term in order to include the anomaly. So the so-called K current. So if you can you can have a globally conserved J mu plus K mu, right? So if you have a conserved axial current, then this is a completely, say, independent, say, constraint, or completely independent conservation law, if you want, compared to angular momentum.
Right.
So I fully
angular
agree.
Momentum must be conserved for any theory, right? So
yes, absolutely. Yes, I agree. In fact, this is
also that's also what's confusing to me. The other thing that is confusing to me that we have been, and also many people, many of you who are doing spin hydro have been continuously, focusing on the spin tensor. But on the other hand, if one think about this, spin really is not conserved, physically speaking.
I think there will be a devoted session to this for this program.
Yeah. Sure. I saw the program. Yeah.
Yeah.
Yes.
Yeah.
Can I say something? Hi.
Yeah. Go ahead.
Yeah. So what is the problem if the spin is not conserved? I mean, it's true that it's not a proper hydrodynamic mode in this sense, but somehow the total angular momentum is what matters, right? So the point of view is that you look actually at the total angular momentum conservation, not really at the spin non-conservation, if you wish, if you really don't like to talk about spin tensor. So I think,
yes, that's right. I mean, spin tensor, of course, is a dynamical quantity. You can always compute if the expectation value from quantum field theory or from Wigner function. That's fine. But when we talk about hydro in the usual sense, we formulate hydrodynamics in terms of variables that are conserved quantities. That's mainly what I'm trying to say.
I think that also depends on how you choose what is called the pseudo gauge. In some cases, if the T mu is symmetric, spin tensor is actually conserved.
No, that's fine. But that spin tensor is not exactly the kind of spin we usually have in mind, right? I would say.
Why? It depends. I mean, somehow you assume that it's a sort of density when you average, it gives you some spin, which is what we have in mind. So the thing is that the problem is that how we
add something. It has something to do with the definition of the local equilibrium, with spin, and I think that so this is what will be discussed in the next days by many people, including I think Enrico, Abdesh. But if the collision term is local, which is kind of strong assumption, then the spin part is separately conserved, and or if the collision term is local, then it makes sense to introduce the chemical potential related to spin directly, because it's conserved in collisions. So I think under assumption that the collisions are local, and so there is no spin orbit interaction, I would say. So for instance, hadron gas, mainly interactions are mediated by pions, kaons, then I think we can well define the local equilibrium, and then the I think we can have equations, hydrodynamic equations for the spin chemical potential, because we have 6 equations and they always exist. Independently of the pseudo gauge, you know, they always exist, and actually the hydro equations are the same, only the localization of energy density and spin density is different. But this is well known, I would say, in field theory.
So the thing, yes, I agree. I mean, the thing is that what we mean by spin tensor, if we want to say that has some physical meaning, and so how to probe in case what a spin tensor is in case, right? So I think that these are questions that we don't have a definite answer, but somehow we believe that if a spin tensor, as Wojtek was saying, is a spin density has to change if there is this what we call the spin orbit interaction, what transfers, so this mechanism that transfers the orbital to the spin angular momentum, then somehow we need to assume that there are some non-local collisions, and I would say that somehow a physical picture would be that the spin tensor would not be conserved when there are non-local collisions, and this is what we got in a specific pseudo gauge somehow, and this is what I and Nora will show during this talk, I think.
Yeah, but we also found that somehow there are sort of 2 levels of this, you know, spin conservation or non-conservation, because, for instance, if we have canonical forms and T mu is not symmetric and the spin tensor is not conserved, so then the equations are exactly the same as if we go to this what we call de Groot, Van Leuven, Van Wert pseudo gauge, where T mu is symmetric and the spin tensor is conserved. So I think there is some, you know, there are 2 levels, I would say, of the discussions of this problem, that you can use pseudo gauge and actually there is some class that you have always the same equations, only allocation of energy density and spin density are different, but the equations are the same. But okay, so then if you have 6 equations coming from the angular momentum conservation and you assume that there exists something like local equilibrium, which is defined by 6 parameters, then somehow you can construct simply, you know, effective theory for the 6 degrees of freedom. And I think this depends on this kind of assumption that the collision term is local. And I think this is known already from very ancient times, because this was discussed by the papers by Waldman, I think, who was working on kinetic theory with spin in, I think, 70s or 60s or even 50s. Yeah. So now there is this kind of breakthrough by Enrico and Nora and Dirk that somehow they include these non-localities, but they also somehow say that this kind of concept of local equilibrium is kind of maybe ill-defined, or somehow maybe it should be redefined in some way, somehow, if you have non-localities. So this will be good point for the discussion I'm waiting for.
Maybe we should discuss it when
it's time.
When the respective talks are given then.
Yeah, sure.
Okay, so let's see. So we had some comments on we had an advertisement for Zubarev by Francesco, and we had also some discussion of entropy current, but related to Zubarev and also now spin currents. I don't know. So Masoud, I think your question is somewhat unrelated. No? You are more, you wanted to know what's the role of electric fields in the CME, or?
First, I want to thank for the comment on my question, because at the time I couldn't turn on the video, the audio. What I wanted to say is that the relation between between separation of charge and CME is based on the idea that there is no electric field and the whole quark plasma is not locally charged. Please correct me if I'm wrong.
At high energy, that's perhaps almost true, I guess.
But I don't think I don't think that in the relevant energies, I mean, if you look at the lattice results, the electrical conductivity is not very large. It's, for example, it is.
Correct.
Let assume that it is 20 MeV. Okay, so if you look at the this is the electric both the electric charge and the electric field should be exponentially suppressed by a factor of like e to minus sigma t. Okay, and this is actually something that we can deduce in a simple setup. If that is so, the lifetime of the Qualcomm plasma is much smaller than the relaxation time that for the charge density and the suppression time for the electric field. So if that is the case,
the electric field, I mean, all the strong initial field come from the ion. The ions fly away very quickly, especially at high energy. So both that electric and magnetic field from fast-moving ion decayed fast. The difference between electric and magnetic is that I believe there is some hope that the magnetic field could be a little longer. I guess that's
yes.
what,
I mean the ratio of these fields is not actually that suppressed, in my opinion. And
if you look into the slides, so for the slides of my talk that's now, I think it has been posted online. We actually solve Maxwell equation with both the electromagnetic fields. So they're both dynamically evolving according to Maxwell equation. So we do have those information, But I doubt it would induce any. Well, it could. I mean, it could induce some effect, but we haven't looked at what exactly it could lead to. And also the other thing is that magnetic field. If you look at the geometry of the collision, magnetic field add up coherently, meaning that they are both pointing up from the two ions. But for the electric field, they're sort of canceling each other between the two ions.
Yes, but CME is an event by event phenomena.
No, what I mean is the event by event simulation. I mean, anyway, so the electric field are computed actually. So that's pretty short. So whether there's some interesting effect coming out of that, that's a question that of course need to be looked at, I guess.
Yeah.
And also the electric charge.
I think there are some microscopic calculations of this. But I think it was not so conclusive.
Yeah, at 200 GeV, the charge density in the middle rapidity is very, very small.
Yeah.
If not exactly zero,
can I make a comment about this? So the electric field, indeed, I think I definitely agree with Masoud that if you just do a simple calculation of by solution of Maxwell's equations in the presence of some small conductivity, indeed it takes a long time for it to decay. So but this is as Jingpeng said, that this is all included in the simulations, so that's
right.
fine. But the only point that I want to make here is that there are many papers that are doing more formal calculations in the hydrodynamics that include, so this magnetohydrodynamics, for example. I think there as well, the electric field should be taken into account. So in most of these calculations, the magnetic field is taken as order 0 in derivatives, but electric field is taken as order 1. But I think that that doesn't really apply. That situation doesn't apply to quark-gluon plasma. So as Masoud mentioned, I think they should be of the same order. I mean, okay.
Yes, and if you take electric field at order 1, then the gradient of the chemical potentials is also as order 1, which may not be a good approximation again.
I mean, this is, if you expand the, then you can expand around equilibrium. No? I mean, if gradients are order 1, then there is no real equilibrium. No? All these approaches make the assumption that you expand around some local equilibrium state. And then the counting is order small, electric fields order small, and magnetic fields order 1. Because in magnetic fields, you of course have well-defined equilibrium.
Right.
But if you write like something like E mu is equal to, I think, T d mu over T, you can have E mu at order 0.
Yeah, but
look, I think if we are talking about magnetohydro, so sort of the starting point is that you're assuming the conductivity is large enough so that magnetic field will be dominant. I think, and I think that approach is consistent by itself. The only thing is that whether it's applicable to nuclear collision or not.
Yeah,
I
exactly.
agree.
I think it doesn't really directly apply. So it's not a, I mean, it's an approximation, but it's not the perfect approximation too.
Yeah, so that's right. So we have to separate between the applicability of a theory and the limit where you actually derive a theory. And there may be a gap. That I agree.
But you see, so for example, there are insulators which you can also study by using hydrodynamics, and there you take electric field to be order 1, because in those cases there's no chemical. I mean, so it doesn't decay the electric field because there's no moving charge degrees of freedom, so the electric field stays.
It stays there, yeah.
Yeah. So so that it is. I mean, that can also be done using the hydrodynamic approximation.
That's interesting, yeah. Okay, but this kind of took us a little bit away from the other questions. I don't want to extend this too much beyond 6 o'clock in Europe, because we have had a long day already. I think also Giorgio had some other comment here in the chat, and also there was Golam had also some question about the formalism of Umut. But let's see.
So I was whether.
I mean, so that was. You don't go to gradients, no? In your formalism.
No, we do.
Not second order, first order.
Not second order, first order. But that can be, that in the formalism itself, yes, there is room for. I mean,
there is room for that.
I mean, in the gravity theory, you don't have a choice. You have everything. So it's in the holographic theory, you have all the orders. The only question is to identify them with the corresponding holographic derivative expansion. But you have all of them essentially in the full solution. You have all of them.
I have. Can I make a comment?
Sure, go ahead.
Yeah, I mean, I'll just say it out loud. It's a bit different from a gradient expansion. The point is, I mean, this is sort of goes at the basis of statistical mechanics. Vorticity is a collective mode, and spin alignment, polarization, spin alignment, and stuff like this is something that affects microstates. It's an individual mode. So this is something that things talk to each other. I mean, the large NC effect is a symptom of this. I mean, this is correctly capturing the fact that the semi-classical limit happens when the microscopic orders, the degrees of freedom are separated from the macroscopic ones. And I mean, Nora's calculation is the other limit of this. I mean, the fact that molecular chaos is in a sense broken when you're thinking about spin-orbit interaction. So this is what I'm worried about. It's the fact that it's a very non-trivial phenomenon because microscopic and macroscopic effects mix.
Right. Yeah, definitely. But this is a different question, right? So we were just so that's a separate question. Large n or small n.
It's not great. Yeah.
So in principle, the holographic calculation itself is right. So it's an approximation problem here. So like indeed, I definitely agree that at large n there's a suppression. So can we approximate? Can we get universal results that are kind of that can be captured by this Largan approximation or not, it's a different thing. But indeed, in the end of the game, so you have to include all the 1/n square corrections. I agree with that. But my point was that just like in the charge flow, the charge current itself is also made out of the constituents. But then in the hydrodynamic approximation, there is a conserved degree of freedom, a collective degree of freedom, which you can calculate by solving hydrodynamic equations, which can be mapped onto this holographic calculation. So here I'm just saying the same thing. Modulo the fact that, okay, if you have an antisymmetric part, the spin tensor may not be conserved, whatever, but modulo that, there is a hydrodynamic equation, and that this can be mapped onto a holographic calculation. So you can derive essentially this hydrodynamic equation from holography.
Let me also make a comment as far as polarization goes. I completely agree with you, Giorgio. It's so if I'm used to this H bar counting, so polarization is actually H bar squared. Okay, while all the other effects that people have been talking about are H bar effects. Polarization, you have to have spin-spin interactions to polarize or magnetize a medium. And actually, it was really elucidating to look into Landau-Lifshitz volume 5, and you can actually see that the first order H bar will cancel precisely between states of spin up and spin down, but magnetization or polarization arises from H bar squared order effects. That was really very good, very insightful. So if you like, take a look. I mean, Giorgio probably knows this.
Sure.
That's where
I
came up with this. But
we have to discuss this. Actually, I am just because we did.
My only complaint is that it's not H bar equals 1. It's state occupancy expansion.
George, have you ever learned about WKB, semi-classical method?
It's deviations from WKB.
Expansion works, but should be understood properly.
Giorgio, one thing, when we say H bar expansion, we always mean an H bar gradients expansion.
I know.
So
I know.
Enrico, but H bar times the gradient, it has still the dimension. So it's
no, I know. I'm not saying that I'm not saying you're wrong. I'm just saying it can be confusing. I mean, I completely agree with what you guys do. I just think that some people might find confusing when you say H bar expansion.
Okay. Well, in any case, I mean, large N or small H bar should somehow be the same of the same order. I mean, this should be similar. That's why that was why you were asking this question. Large N is mean field, basically, no?
Yes. Yes, exactly.
Yeah.
Okay, I have to look into Landau-Lifshitz. Yeah.
Oh, this is so beautiful, Wojtek. You will always enjoy this, of course. Looking at this.
No, because I think.
Yeah, I can
doing something different. So I'm afraid you want to say that we screwed it.
No.
In which volume? In
no. Volume 5, Statistical Physics. Volume 1, Statistical Physics 1.
Okay.
Wait a second. No. What I'm saying is because we were trying to understand this polarizable media, we actually, if you don't take if you have to take both spin states into account, and you have to go to second order in the magnetic, in Bohr's magneton or in H bar. Otherwise,
which page is it? Right.
Oh shit! Wait a second. I have only the German version. Shit. It's really this discussion about magnetization in gases, in Fermi gases. Okay, let's see.
Which section is it?
Yeah, I'll try to find. Oh my god. Okay, where is it? Is it somewhere 56? No, wait a second. Ideal gas should be, no. And now it had, here, okay. Magnetism of the electron gas. Paragraph 60. It looks like 60 to me here. Is this where it is? No, I think that there must also be a classical discussion based on Boltzmann distribution.
It's the first volume of statistical physics.
It's the first volume. Yeah. Okay, let's see here. Monatomic gases. Okay, let's see. There's a discussion about hold on. Here, okay. It's chapter 52. That's it, 52. That's the thing you want to look at.
Okay.
Magnetism
52.
of gases. Magnetism of gases.
Okay.
I can tell you why we came up with this. I mean, so we were generalizing this this old work by Israel, no? The dynamics of polarized fluids or something, or this old paper, and we wanted to add dissipation to this, and then we said, okay, in this framework you have to get the right susceptibility, no? For the electron gas. And we were not able to get it. And the reason is you have to take both spin states and you have to go to second order, because in between, at first order, they cancel. No? What the spin up guys will align parallel or anti-parallel to B, and the spin down the other way. So that contribution to the
Would that only for magnetic field or also for rotation?
Magnetic field. Rotation, I don't know. You have to check. Rotation should add up, no? Isn't it? Or
yeah, so that's the issue of Francesco all the time. That magnetic field somehow acts completely opposite way than equilibrium, equilibration.
Yeah.
Because if you have the spins, okay, if you have the magnetic moments aligned, then the spins are opposite. If you have particles and antiparticles, yeah. So if you, for instance, have baryonic free matter, then you will not polarize it with magnetic field, because you have the same number of up.
Down.
Yes.
Yeah, but
in equilibrium, okay.
If you go to second order, you will. This is the second order effect.
Yeah, in the second order, yes. Okay, right. But
that is what you call para or diamagnetism.
Okay, right. Yeah, which is weaker than. Yeah.
It's a weak effect. Yes.
Yeah. Okay. So we are doing some. Okay, so I now think that we do something like paramagnetism. Somehow the number of particles somehow somehow compensates the smallness of h bar. If we but this is another topic.
Gets more. Okay, I'm not so sure, but I think we should call it a day for now.